This video is going to talk about what is called the epsilon delta definition of a limit. Now, in case you aren't fluent in Greek, this symbol here is epsilon, and this symbol here is delta. That's why it's the epsilon delta definition. Now, you might complain that we're using Greek letters here instead of just a regular A, B, C, D, or whatever here. This is kind of a holdover for a long time in mathematics. One of the first ever theoretical textbooks that influenced a lot of mathematicians was written in ancient Greek. And then when the Europeans were kind of adding on to that, they decided to, honor the original works by using Greek letters in them, and they've stuck for several hundred years now. We're probably not going to be able to get rid of them, so you have to just get used to them at this point in time. I will say that this video, this topic here, is, in my opinion, the hardest theoretical concept in the entire calculus class. It's kind of really out there. We're going to be doing mathematical proofs in this section, so keep that in mind here. So this that I've written here, this is the true definition of a limit. Previously, we've been doing things like looking at graphs and plugging in values, and those work pretty well, but this is the true mathematical definition. And the reason why we have something like this, it's this complicated, is that initially, if you go back a few hundred years, when people were doing limits, they were just kind of doing hand wavy. They were just trying to, looking at the concept rather than the details. And what turned out is they were running into problems. They were getting these answers that didn't make sense. And so they had to go back to the beginning and say, well, what can I do to make this really precise so that I will always get the right answer? And it turned out that this right here was the thing they needed. And it's unfortunately complicated, but as I said, it was the requirement to actually get anything done. So let's kind of break it down here. So the first part of it is saying the limit of a function equals the number L means blah blah blah. And it says for every epsilon greater than 0, there has to exist a delta greater than 0 such that whenever this weird inequality is true, we must have this other weird inequality is true. Well, to go into more detail on this, if you ever have the inequality x minus a is less than, let's say, for example, 5, what that means is if you go on your number line and you start with a in the middle, then what you're going to have to do is you're going to have to go 5 to the right and 5 to the left, and you're going to take all the numbers in between those. So whenever you have absolute value x minus whatever a is less than some number, let's say 5, then it's going to look like this. And if you have absolute value of x minus a is less than, now say, let's say delta, it means on your number line you start at a and you're going to go right a value of delta, whatever number that is, and you're going to go left a value of delta, whatever that is, and look at all the numbers in between there. Similarly, if I have f of x minus some y value, let's call it L, is less than 5, that means if I do a number line of y values here, and I pick this L to be the middle, then that means I go above it by epsilon and below it by epsilon and look at all the things between there. I'm sorry, I meant 5 there, but it's going to be epsilon. Right, so again, here's the other one where we're less by a value epsilon. We look at our y-axis here. We look at L. We go up by epsilon and down by epsilon. And there we go. Now, how are we going to put this all together here? The idea is we're going to look at our graph here of whatever function we may have. So here's my function. And we're trying to find the limit of this function at a value x equal to a. And based on our picture here, this y value up here, that's going to be exactly the limit, which we're calling L here. And what the definition says is that no matter how little, epsilon is usually going to be a small number, no matter how close you want to be to this y value L, there's guaranteed some distance on your graph where you can go left and right, and the y values are always going to be in the purple band. So the idea is you have a graph, you have a value that they give you, you have the limit that you have, and the idea is that no matter how close to the limit in purple you want to be, you guaranteed are going to find some sort of a green area on the x-axis where the entire green area is going to be contained in the blue area. Sorry, purple area. Apologize for that. And so what do I mean? What if I redo this? What if I look at like the same kind of graph here, but now what if I want my purple area to be really, really, really narrow? The idea is even if I make it more narrow, there's a possibility that I can just make the green area even more narrow, and it will still have the case that the entire green area is contained inside the purple area. So that right there is the precise definition of limit, is that no matter how small of a purple area you find, you are guaranteed to find a corresponding green area on the x-axis where the green area is going to be entirely inside of the purple area. There is one thing that I've been skipping over though, and that's this 0 less than. So what that means is that you cannot have x minus a being equal to 0, which would mean x equal to a. So that means that we don't actually care what happens right at that point. We only care about what happens nearby. So if you have a weird function where it's looking fine and then there's a hole, and then you have a weird jumping point way over here, and you say, well, okay, let me go ahead and take my purple area around this part, and I want my green area to be completely inside of that. You might be like, wait a second, I've got this point up here that's not inside the purple region. But what I'm saying is that because of that extra 0 part right here, it means that we don't actually care about a single point being out of the way as long as everything else nearby was within purple. And the reason why we have that is so that way we can still find limits when you have piecewise functions with weird extra points here. If you did care about what happens at that point, then limits of something like this would not work, and we want limits like this to work. Now, let's do an actual example of this. Let's do the following here. Let's prove that the limit as x goes to 2 of the function x plus 3 is equal to 5. Now we know it's 5 because we learned in previous sections that we can just plug in the 2 and get 5, and that's going to be the right limit. But now we need to mathematically prove it. And the thing is I'm going to give you a template right here that will work perfectly fine for any linear function like this. And really, you're going to want to just learn this template and then fill in what you need here. And it's always going to start by saying let epsilon be greater than 0. And the reason why is we need to make sure that no matter how small epsilon is, that this whole process is going to work. And so that means we're going to leave epsilon as kind of a variable that can be as small as possible, and we need to find our answer in terms of that variable epsilon. Now we need to choose the value of delta that's going to make this work. And I'll give you kind of a general rule here. If you have any line here, you're going to choose delta to be epsilon divided by the absolute value of the slope. And the reason why is, if you look at your picture and you try to say is, well, okay, if I have a certain range of y values right there, what should my corresponding range of x values be? You're basically looking at a slope triangle, and that's where it's going to come from. Now I will say that this only works if you have a line function. It would not work with anything else. Anything that's not a line, you have to go through the whole process and figure out what your delta is going to be. But all I'm going to require from you in this class at least is doing it for a line. Now in this case, for the x plus 3 example, my slope is 1. So delta is going to be epsilon here. Then we would say then if 0 is less than x minus 2 is less than delta, we must have absolute value f of x minus L. Well, my f of x function is x plus 3. I subtract my L, which is 5. And if you simplify this, this is going to be the same as x minus 2. And by our previous statement, that is less than delta. But delta is actually equal to epsilon. So I just showed that f of x minus L is less than epsilon. And I'll make a little side comment here. That means y values are all in purple region. And so therefore, we're done. Therefore, the limit as x goes to 2 of x plus 3 equals 5. And you're going to want to basically take the same template, fill in the different values here, and play around with things. Otherwise, it will all work out and give you the answer. Keep in mind, once again, this template and everything here is only going to work for linear functions. If you have like an x squared or something else more complicated, it's going to be even a much bigger nightmare to work out. But thankfully, we don't really need that at this level of mathematics.